In this video, we are going to see applications involving exponential functions. So we know for exponential functions, we have either if the base is greater than 1, then we have y equals b to the exponent x. If b is greater than 1, it's increasing, and if b is less than 1, it will be decreasing. And these are the two types of applications involving exponential functions. If it's growing, we call it exponential growth, and it applies to b is greater than 1. And if b is less than 1, then it will be exponential decay. And when greater than 1, we could write it as 1 plus a growth rate in percentage. If it's less than 1, then we could write it as 1 minus a percentage. We call that percentage is decay rate. And a is initial value, because when x equals 0, you will have b to the exponent x equals 1. So the y equals a value, that is 0, comma a, that is on the y-axis. So that is a y-intercept, initial value. And y is a total amount of numbers for the stuff that we are investigating. So x is a number of growth periods or decay periods, either in years or in hours or in days, is time. And this is a general formula for the exponential growth or decay. And also there are two special cases. One is base equals 2. So when the base is equals 2, from that general form, we have y equals a, then 2 to the exponent x. We write x as a time counting by doubling period. So when t equals d, then it will be 2 times a is doubled. So the d is counting by the doubling period. And another special case is the base is 1 or 2. We call it involving half-life. So y equals from the general form, then base changes to 1 or 2, then the time is counting by half-life. So you don't have to memorize these two formulas. These are just the same as y equals a times 2 to the exponent time divided by d, or a times 1 or 2 to the exponent t divided by h. They are equivalent, just in different format. So now we are going to see where we could use exponential growth or decay to solve applications in real world. So the number of a certain bacteria doubles every 5 days. When you see the keyword doubles, then we know we could use a general formula a to the base is 2, then the time is counting by doubling period. So from the given information, we could know that d is 5 days. And the initial population is 15, so the a value is 15. And the question A asks you, determine an exponential model for the number of bacteria after t hours. So the t is in hours, and the d, if we want to change it to the same unit, so we could change 5 days. Then we know that 1 day equals 24 hours, so we could put 24 hours on the numerator and 1 day at denominator. So 1 day equals 24 hours, we times by 1. We didn't change anything, but we could cancel the units, days out. Then you will have 120 hours left. So when you are doing the unit conversion, you could always use this method that you need to times 1, but you want to cancel the 1 unit out, so you will be able to determine you want to times 1 day over 24 hours or times 24 hours over 1 day. So now we are going to sub in the A and the D value to this general formula. Then it's 15 times base is 2 because involving doubling period, so T over 120. This is answer for the question A. This is exponential model. 15 is initial and base is 2, so every 120 hours it will be doubled. So question B asks you to determine the number of bacteria after 7 days. So T equals 7 days now. And the same thing, we want to change it to hours. So 7 days times 1 day equals 24 hours. So we put a day at the bottom, 24 hours on the top. So we are going to have 168 hours. Then we sub it in, the number of bacteria equals 15 times 2 to the exponent 168 hours divided by 120 hours. Then equals, we do the calculation, then you type into your calculator, we are going to have 39.59 bacteria. And for the live stuff item, we are going to round it off. So as long as not a whole number, we round it off. So the statement will be the number of bacteria after 7 days is 39. So we round it off. Otherwise, we need to round it up. If it's greater than 5 or equal to 5, we need to round it up. So, but for the live item, we round it off. So this is for the question 1, doubling period. Then we are going to see the next example. So this is involving investment. $4,000 in an account when he was born. The account pays interest at 6% / A means annually. Compounded annually. So how much money will be in the account on Rwanda's 18th birthday? So question A, this one, we are going to start with a general formula A, B to the exponent x. And this one we know it is increasing, so the base B is 1 plus the growth rate R, that is your percentage, 1 plus 6%. It will be 1.06. And initial value is the current amount of money is the very beginning amount of money is $4,000. So the X is 18 years. So we sub in all this given information, we are going to have Y equals $4,000 times 1 plus R, 6%, then to the exponent 18. So you have 4,000 times 1.06 to the exponent 18. Then get your calculator out, type into your calculator, then you will have $11,417.36. When it's involving in dollars, we keep 2 decimal places. That is 36 cents. And this is for question A. For question B, it asks you if they want to have $15,000 in the account. It asks you what's interest rate they need to invest. So we are going to have y equals, this is a total amount is 15,000 and initial amount is still $4,000. So in this equation we have y equals a, then 1 plus r to the exponent x. So b is 1 plus interest rate. So we sub in x is still 18 years. So we sub in this given information, we are going to have $15,000 equals 4,000, then 1 plus the interest rate to exponent 18. So in order to solve for r, we move the numbers to other side by doing opposite operation. So 15,000 divided by 4,000. Then we are going to have 15 over 4. 15 over 4 equals 1 plus r to the exponent 18. Then we get rid of the exponent 18, we do the opposite operation, will be take 18th root. So both sides we take not square root but 18th root, 1 over 18. Then you will have 1 plus r, 18 times 1 over 18 give you 1. So you have 15 over 4 to the exponent 1 over 18. Then we want to solve for r, we move the 1 to other side, will be minus 1. So we have 15 to exponent 4, then 15 over 4 to the exponent 1 over 18 minus 1 equals interest rate. Get your calculator out, you will find out it is 0.076 equals r. Write it in percentage, will be times 100 is 7.6% equals r. So then we know that the interest rate need to have is 7.6%. Then at the end of the when the remainder reaches 18 years old, the account will have $15,000. Okay, so this is exponential growth involving the investment. So the A value is initial value and B is growth factor, 1 plus growth rate. So when you want to solve for the interest rate, we keep moving the numbers to other side, isolate r, because r appears only once. So this is example 2, applications of investment for growing exponential growth. And this one is exponential decay. So 320 milligram of iodine 131 is stored in a life for 40 days. At the end of this period, only 10 milligrams of the element remain. So it asks you to write an equation for the iodine 131 remain worst time. So question A, we are going to write Y, write the general formula out, then after that we are going to determine A is initial value is 320 milligram, and the B value is unknown. So X is 40 days. So we could write it as Y equals 320, then B to the exponent X. And the question B asks you for the half-life, so we could write it as a half-life. So Y equals, the B will be 1/2 to the exponent T over half-life. And if we sub in the given information, you will have this Y after 40 days, Y is 10 milligram. So we could set up an equation. It will be 10 equals 320 times the half-life T divided by 40 over half-life H. So this is a equation for this, convert the sentences into this equation. And when we want to find the half-life, we could bring the numbers to other side and try to solve for the exponent. This is exponential equation. So we bring 320 to other side. Then both sides need to be opposite operation is division. So we are going to have 1/32 equals 1/2 to the exponent 40 over H. So you could use a same base. So 32 is 2 to the exponent 5. So we have 1/2 to the exponent 5 equals 1/2 to the exponent 40 over H. If 1/32 is not a 1/2 to the exponent integer, you could guess and check, put a number close 1/2 to exponent, then see when you will have 1/32. So when you try it, we are going to do is try only the denominator, 2 to what equals that one. So if not integer, you could try the decimals. Then after that, we have the same base. We could let the exponent equal, because exponential function is 1 to 1. You have the same exponent, then you will have the same power. So when we solve for this one, we could do the cross multiply. 5 times H equals 40 times 1. Then bring the 5 to other side. You have H equals 8. So we know the half-life is 8 days. Then this is a question B. For question C, it asks you T equals what? When, how long? It will have 30 milligrams of the element left. So we sub in 30, that equals 320, 1 over 2 to the exponent t over 8. So we know the half-life is 8. Then we are looking for the t again. So bring the 320 to other side. We have 3 over 32 equals 1 over 2 to the exponent t over 8. Then you could guess and check 1 over 2 to the exponent what is close to 3 over 32. So guess and check and try the different numbers. So we try the 3 divided by 32, then give you 0.09375. So we are going to try 1 over 2 to the exponent what give you the 0.03975. So 0.1 over 2 is 0.5. We try to the exponent 3, it is 0.125, so we know that is a decay. So 3 is here, then we need a bigger number to make the number smaller. So we try the 4. So 0.5 to the exponent 4 give you 0.625, so it is too small. So we need to find a number that is between 3 and 4. Then we try the 3.5. So we keep going to the middle, to the exponent 3.5. Then you see this number is smaller, so we need to have a 3.5 is here, not that one. So we need a number around this 0.09. So we need to go smaller. We are going to try the 3.4. 0.5 to the exponent 3.4. Then give you 9.4. So it's bigger. So it should be between 3.5 and 3.4. So we try another number. 3.45. 0.5 to the exponent 3.45. Between the two numbers is 0.015, so it's bigger. We need to make a smaller. 0.5 to the exponent 3.425. Between the 3.4 and the 3.5. That is still smaller, so need to be less than 3.425. We are going to try the middle of 3.125. Then it is bigger, 0.5 to the exponent 3.415. So this one is close. So 1 over 2 to the exponent 3.415 equals 1 over 2 to the exponent t over 8. Then we could write the exponent equals, so 3.415 equals t over 8. Then we bring the 8 to other side to solve for t. Do the opposite operation is multiplication. So 8 times 3.415. Then we have the time equals 27.32 days. Then write a statement. Therefore, question B is the half-life is 8 days. And C, after 27.32 days, there are 30 milligram left. then it is done. And for the question C, also you could use a log to do it. So exponent equals log power over log base. Then we have t over 8 equals, from this equation, log power is 3 over 32 over log 1 over 2, and it will give you 3.415. Then go from there to solve for t times a to other side. You will have the same answer. So in this lesson we have done the general formula a times b to the exponent x, and based on the half-life, then t counting by half-life. The base is 1 over 2, and if double life, then it will be base is 2. If it's a growth, then plus the growth rate. If decay, it will be 1 minus the percentage decay rate, and go from there. When you are solving for the exponent, that is exponential equation, then you could try the common base, same base, then exponent equals, or you could guess and check to find the common base to the exponent, or you could use a log to solve for the exponential equation. And if you are looking for not exponent, you just look for other numbers, then you could just doing the opposite operation to isolate the variable if the variable appears only once. Thanks for watching.